All right, anybody have any homework questions? No? Okay, so we're getting into particle kinematics, particle statics. Um, part- Kinematics and statics is really easy. Everything's just zero, so it's really particle statics we're getting into. And I gave you a couple of problems to work on. I'm going to say a couple of things that hopefully will sort of clarify some of the ones that you've been working on, and then we'll do a bunch of example problems. So one of the, I don't know, three major concepts in this class are joints. So when you're dealing with contact forces, first look at joints. You can think of a joint as any connection between two bodies. I suppose it can be more than two. And a joint in this class is defined by what type of loads it applies to the connecting bodies. So we'll define each joint by the type of loads it applies to the connected bodies. And as we go on, I'll give you long lists of different types of joints that we're going to use over and over and the kinds of loads. For particle statics, there are just three that we need for right now. So the first three are first cables. And all cables do is apply a pulling force on the body they're connected to. Second type of joint is frictionless contact between bodies. And that's just pushing force. And then the third one is friction contact. And that's a pushing contact plus other stuff. The other stuff is the friction. And so mathematically, I'm just going to go through these three and talk about how to treat them. So first, cables. We are only going to be dealing with massless cables. That cross over massless frictionless pulleys. It sounds like a lot of assumptions to make, but it's usually a pretty reasonable assumption. So the force that a cable applies to a connected body is parallel to the cable and away from the chosen body. And third, the magnitude of the force is the same all the way along the cable. Okay, so for example, if you have a pulley hanging from the ceiling and it's connecting two hanging masses, so let's say that's 2 kilograms, that's 1 kilogram. Free body diagram of the 1 kilogram mass looks like 1 times 9.81 down, that's the weight. And then the cable force is parallel to the cable, away from the chosen body. And then the free body diagram of the other one this is the 2 kilogram mass. So the weight is 2 times 9.81. And the force is parallel to the cable, away from the chosen body. And the magnitude of the force is the same as it was on the other side of that cable, since it's one cable passing over nothing but massless and frictionless pulleys. The next type is frictionless contact. That's a pushing force. And if two objects are pushing on each other, in frictionless contact, the force is perpendicular to the surface of contact and second, toward the chosen body. So pushing and pulling are opposite that way. Cable force is applied away from the chosen body. Frictionless contact is toward the chosen body. So for example, If you have two carts on an incline, say this one's 3 kilograms, this one's 5 kilograms, and let's say there's another external force of 100 newtons applied to the 5 kilogram box. Then a free body diagram of the 3 kilogram box looks like this. There's the weight. So 3 times 9.81, I'll just write that as 3G. And now we're looking around the boundary for contact. At the wheels, there's a pushing contact. The ground's pushing on the wheels. So that force is going to be perpendicular to the surface of contact, the ground in this case. And, you know, saying it's perpendicular means that it's either going this way or this way. And then since it's a pushing contact, it's toward the chosen body. So that fully defines the direction. And I'll call that N3 for the normal force on the 3 kilogram. And then keep going around the boundary. Look for other contact with the outside world, and the only other place is on the right side. That's another frictionless contact, a pushing contact. So that is perpendicular to the surface of contact, toward the chosen body, and I'll write that as R. Those are just variables. So now let's think about the 5 kilogram. There's a weight of 5 times 9.81. There's a pushing contact ground. That's perpendicular to the surface toward the chosen body. I'll call that N5. That 100 Newton force is applied on the right side. That didn't appear on the 3 because it wasn't applied at the boundary of the 3. And then over here, we have the force that comes from the same contact as this. And so Newton's third law says we're going to keep that same variable name and just flip the direction of the force. So this. And that's also a pushing contact, so it ends up being perpendicular to the surface of contact toward the chosen body. So this and this have to satisfy Newton's third law. That's the magnitude of the contact force between the two bodies. And Newton's third law says it has to be the same magnitude. The force, which ones? 3G and 5G? Oh, N3 and N5? Yeah, they don't, they're in the same direction because the direction of the incline is the same here and here. But both of those forces are perpendicular to the direction, perpendicular to the surface where that contact is happening. So yeah, since this thing is at the same angle the whole way down, perpendicular to the surface here is the same direction as perpendicular to the surface Gravity is straight down. Yeah, those normal forces are not straight up. They're perpendicular to the incline. Okay. Yeah. Any other questions? You know, once you get to the free body diagram, you can, since the only things on it are forces, I guess I usually leave off the units. Like on the diagram that introduces a problem, I'll put the units on so you can tell what's the distance and what the force and whatever. But the only thing left here are forces and couples, and you can tell that from the figure. But I think that's just the habit I've gotten into. I don't think that's like any real kind of thing, you know. Any other questions about that? And then the last one is friction contact. Um, and when there's contact between two bodies with friction, it applies a force with an unknown direction. So force vector with an unknown direction. So for example, if you have an incline and a 2 kilogram box sitting on the incline, and a 1 kilogram box on top of the 2 kilogram box, and let's say you have a horizontal force applied of 5 newtons to the top box, and then a force parallel to the surface applied to the bottom box of 10 newtons. And let's say both of these contacts have friction. Then a free body diagram of the there's no 5. The 1 kilogram box. There's a weight acting down of 1 times 9.81. There's a horizontal force of 5 newtons. And the only other place that there's contact between the boundary and the outside world is at the bottom of this box. That's a friction contact. So I'm going to draw 2 vectors in the direction of the coordinate axes. And I'm going to label this the force vector on 1 by 2. And then the free body diagram of the 2 kilogram box. We have the weight of 2g. We have the 10 Newton force. Down at the bottom, we have the friction contact with the ground. So I'll write that as the force on the 2 by the ground. And then at the top, we have the same contact force that we saw in that first free body diagram. you can think of it as, it's the force on body 2 by body 1. And Newton's third law says that that's equal to negative F(1)(2). So this is how we're going to do it. If we have two bodies like this and we have to do free body diagrams and Newton's laws for both of them, we're going to represent one of them as like F(1)(2), one of them is negative F(1)(2). What's the benefit of doing that as opposed to calling this one F(1)(2) and just leaving this one as F(2)(1)? So the benefit is just that we're going to get two equations out of this, two equations out of this. That gives us enough information to solve for 4 variables. If we leave this as F(2)(1) without recognizing that it has to be equal and opposite to F(1)(2), we've given ourselves an additional two variables to solve for that we don't need. And chances are we don't have enough equations to solve for it without knowing that relationship. So what this does is it reduces the number of variables and lets the number of equations that we have go farther, Yep. Yeah. Yes. Yeah. Yes, you can. It's just that if you think of this as 4 equations with 1, 2, 3, 4, 5, 6 unknowns, you can't solve the system. If you think of it as 4 equations with 4 unknowns, you can solve it, And that's a big difference, Can and can't that's. Any other questions about that? Okay. Let me go through an example problem. So let's say we have an incline with a pulley at the corner, and there's a cart on the incline that's connected by a cable that goes over the pulley. Okay. Connected to the ground. And let's say the mass is 10 kilograms. And the angle is 30 degrees. What's the force vector applied to the cart by the cable? Whenever you see wheels in a problem, that's meant to it's sort of a shorthand for saying treat that like there's no friction. So this problem is the same as it would be if this was just a box sliding on that incline and it said there was no friction between the box and the incline. So I'll start with a free body diagram of the cart. So there's a weight force of 10 times 9.81, so 98.1 newtons, straight down. Then there's a pushing contact from the incline onto the wheels, and that's frictionless, so we know that the direction is perpendicular to the incline toward the chosen body. All right, that is N. And the cable force is parallel to the cable away from the chosen body, so this way. Okay, so now we have to think about these directions in order to represent these arrows as unit vectors. I'm going to draw the coordinate system, and I'm just going to start writing out the relationships that we know. Like, for example, we know that this vector that's parallel to the incline makes a 30-degree angle with the negative x-axis. I'm just reading that directly off the picture. And then we know that the normal force is perpendicular to this vector I just drew. It's perpendicular to the surface. We know this is a right angle. So that tells us what the unit, it's going to let us figure out what the unit vectors are representing this, the vector in this direction, the normal force direction, and the cable tension direction. So first, to get the unit vector representing that, start at the positive x-axis, counterclockwise to 180, right? So positive 180, backtrack 30, so the angle's 150. So theta is equal to 150 degrees. Now for this one, we're at 150. Backtrack, clockwise 90, so 150 minus 90 is 60. So theta for this one is 60 degrees. Any question about those vectors? So Newton's second law says P times cosine and sine of 150 plus N times cosine and sine of 60 plus 0, negative 98.1 is equal to the 0 vector. That comes out to be negative 0.866 t, positive 0.5 t, plus positive 0.5 n, positive 0.866 n, plus 0, negative 98.1. have a system of two equations. The first one says negative 0.866 t plus 0.5 n is equal to 0. And the second one says positive 0.5 t plus 0.866 n is equal to positive 98.1. This is a system of two equations for two unknowns. You could solve that without too much trouble by substitution. But we're going to be getting into systems of equations of 20 variables, 20 equations. And obviously, you don't want to do that by substitution. So the best way to do this, the easiest way to do it, your calculator does it for you, is reduced row echelon form. So we're going to set this up in a matrix form. So I'm going to write out, so the first thing we have to do is write these equations with all the variables grouped on the left. And all the constants grouped on the right. If you don't do that, you get your answers all backwards. And then we're going to set up a matrix with as many rows as we have equations and as many columns as we have variables, plus another one for the constant. So in this case, we're going to have 3 columns and 2 rows. The first row is for equation 1. The second row is for equation 2. The first column is for, doesn't matter what order you do it, but I'll do t's and then n's, and then the last one is for the constants that are grouped on the right side of the equation. And now in each one of these boxes, we're just going to enter the coefficient of that variable. So in equation 1, what's the coefficient for t's? Yep, negative 0.866. What's the coefficient for n's? Yep, 0.5. What's the constant for equation 1? 0. And now for equation 2, what's the coefficient for t's? 0.5. For n's? And the constant? 98.1. If you enter that into your calculator as a matrix, so, and then run the function RREF. You can write this, enter this in your calculator as, if you have a TI calculator, one of 2 ways. Negative 0.866, comma 0.5, comma 0. Close square bracket, open a new one. 0.5, comma 0.866, comma 98.1. Close square bracket for the second row, and close square bracket for the whole thing. And if you type that in, you'll get an answer. Can someone tell me what that answer is? I don't have that. Oh, yeah, it's a little different in every calculator. Okay, T equals 49.05. Yeah. Okay, and these are in newtons. You can enter this. I think maybe it's only with the TI-89 is RREF, and you enter the matrix as square bracket. To go across the row, you separate with columns again. With commas again. And then semicolon to change the new row. Also, if you have a TI-89, you can use the, I think it's called simultaneous equation solver. That's a little nicer. It actually is a little slower to use, but I use it anyways because the interface is sort of nice. But you want to start getting comfortable using this. It won't be urgent yet. Later on, you're going to have to use it. There's just no way to solve the big systems we're going to have without using your calculator to do it. There is a way. It would take a month. And the tests are less than a month, Okay, so what's the, I asked for the force vector applied to the cart by the cable. So what's the force vector applied to the cart by the cable? We didn't get a vector here. We just got a number for the tension. Well, in Newton's second law, we had to represent the force vector applied to the cart by the cable. It's this. And so now all we have to do is substitute that value of t back into this, and it'll give us the force vector. So the force vector, yeah. Force vector on the cart by the cable is equal to 49.05 times negative 0.866 positive 0.5. And so that is, what do you get? 49.05 times negative 0.866? Negative 42.5? 48. And then this one's 24.25. 24.525. Any questions about that? Okay, I have one more question about this one. What's the force vector? So part B. What's the force vector applied to the ground by the cable? This would be a, really obvious first step towards figuring out if this was a system that you needed to have set up for some reason, and you're trying to figure out how strongly reinforced that floor needs to be. That's the first step, is you'd have to figure out what that force vector is, and then you could use that to calculate internal loads and stresses and whatever stuff we're not doing in this class. Well, the cable applies the same force to everything it touches, as long as it only goes over frictionless, massless pulleys. And so we know that we have a force vector that's straight up, parallel to the cable, away from the chosen body, with a magnitude of 49.05. So the force on the ground by the cable is 49.05 times a unit vector that's straight up, or 49.05 newtons. Any questions about that? There's one question on the homework that I don't think I assigned yet, but I'll assign it today. That asks you. So I'll give a similar example. So let's say we have a box on an incline. Let's say this angle is 20 degrees. And the box has a mass of 20 kilograms. And let's say the box isn't moving. So first, what's the force vector applied to the box by the incline? And second, that contact force that's applied to the box by the incline. In physics, you used to always break that up into two things, a normal force and a friction force. So now let's break this up. What's the part of that force? That's the normal force. And what's the part that's the force of friction? First one in this problem is the easy one. The second one is a little trickier. But I'm going to introduce a mathematical thing we'll use a lot later. We're not going to use it much now. Okay, so first, draw a free body diagram of the box. There's a weight of 20 times 9.81. And then the only other place that there's contact with the boundary is at friction contact. So there's an unknown force vector, force on the box by the incline, FBI. That's where the name of the FBI comes from. I assume. I don't really, that's not based on anything. Okay, so now Newton's second law. So it's sort of funny when you do this calculation, we're going to see that that 20-degree angle doesn't come into this first part of the problem at all. We don't care what that incline is. No matter what that incline is, we just represent that as an unknown force vector. It is going to come into the second part, though. Okay, so Newton's second law says FBI X, FBI Y plus 0, negative 196.2 is equal to zeros. And so the force vector on the box by the incline is equal to 0 for an x component, positive 196.2 for a y component. So now part B. When you did this in physics 1, you would do problems like this by using a rotated coordinate system. And then your normal force was in the y direction and your friction force was in the x or the negative x direction. We didn't do that, right? We used a normal coordinate system here. But now we have to figure out how to break up that. So here's what we have now for part B. We have this force vector that's straight up with a magnitude of 196.2. And we have to break that up into a normal force and a friction force. I'm going to show you the awesomest way to do this. I'm so excited. Okay, so yeah, right. It's so exciting, even though now it's the 50th time I've done this exact same lecture, word for word. It just gets more and more exciting. Okay, so how can we break up that vector that force on the block by the incline vector into the red and blue components that's shown in that picture above? Well, one way, like I mentioned, is if we would have switched the coordinate system to start with, it would have been easy because one's in the x direction, one's in the y direction. So what we're going to do now is we're going to take our answer in one coordinate system and represent it in a new coordinate system. And there's an easy way to do that mathematically. So we want to re-express FBI in a new coordinate system, CS coordinate system, oriented like this. And the way we're going to do that is re-express this vector u, just an arbitrary vector u, and I'll write OLD, u old, that's in the old coordinate system. Given in the old coordinate system as u new in the new coordinate system. First, we're going to find the counterclockwise angle to get from the old coordinate system to the new coordinate system. So find the counterclockwise angle theta to get from old coordinate system to the new coordinate system. In our case, we started out with, so we have it expressed, we have that force on the block by the incline expressed in this coordinate system, the standard one, and we want to re-express it in this coordinate system. So what's the counterclockwise angle to get from here to here? Yep, exactly, 340, or you can call it negative 20. This angle is 20 degrees, so theta is equal to, I'll just write it as negative 20, but 340 works just as well. Now we're going to make fill out a matrix called Q, the rotation matrix, that's always equal to the cosine of that angle theta, sine of that angle theta, negative sine, cosine. And then finally, that vector u in the new coordinate system is equal to the matrix Q times the vector u old, the vector we started with. Your calculator can do that matrix multiplication for you. You just have to enter these things into your calculator. The way matrix multiplication works is like this. If you have a matrix A, B, C, D, and you're multiplying it by a vector E, F, the result is a vector, you're taking dot product, so it's A times E plus B times F, and then it's C times E plus D times F. The top component is A, E plus B, F. The bottom is C, E plus D, F. Okay, so we have, so for us, that Q matrix for this problem is sine of negative 20, negative sine of negative 20, cosine of negative 20. That comes out to be 0.940, negative 0.342, positive 0.342, positive 0.940. And so the force on the block by the incline in the new coordinate system is equal to Q times FBI old, which is 0.940, negative 0.342, positive 0.342, positive 0.940, times 0, 196.2. And what you get out is, what's negative 0.342 times 196.2? I don't have a calculator on me. 67 point what? I'll just call it that. And then what's 0.940 times 196.2? 184.37. So now 184.37 is the normal, 67.1 is the friction force. It turns out that this is going to be a really useful tool in a lot of mechanics classes. We're going to use it all the time in deform. It's maybe more useful in dynamics, although we don't really spend a lot of time doing it in dynamics. And it looks like a pain in the butt when you write out all the elements, you know. I mean, it seems like sort of a tedious process, but in the course materials or course information in D2L, I gave you a list of programs that you can enter into TI calculators. If you put this program in there, it just, all you have to do when you want to do a coordinate system transformation like this is enter in the angle you want. It produces the matrix, multiplied by the vector, and it's really, really fast and easy once you get used to it. Do you remember in Physics 1 do you remember the process for doing those incline problems in the rotated coordinate system? You'd take the weight vector and you'd draw, you know, triangle, or at least imagine it and think about like, okay, that's the cosine and that's the sine and that's negative and whatever. With this, once you get used to it, you don't have to think anymore, you know, which is our main goal. You just take that matrix, multiply it by the vector, and it spits out the answer for you. So it's really useful. And I know you're not used to it yet, but we'll get used to it. Yes. You have to modify the programs a little bit, so come talk to me sometime and we can get those entered so they work. Any other questions about that problem? Yes. The location? Oh, well, there's not really a single location. It's really a load that's distributed over the whole thing. And since right now we're doing particle statics, for these kind of problems, in fact, we're always just going to do particle statics. There's no such thing as different locations, and so that question doesn't come up in particle statics. But it is sort of an interesting question once, if you did want to do that in 3D and figure out, like, so you have this total force of 196.2 pointing up, but it's spread out somehow over the whole bottom of the box. And the question of how it's spread out over the bottom of the box it's an interesting, sort of complicated question that I'm not sure I could get through if I wanted to talk about it right now.
So that negative 67.1, 184.37, that vector represents what?
The friction. That's the magnitude of that is the friction, and the negative just tells you the direction. The y component is the normal force. So the 184.37 is the normal force, and the 67.10 is the friction force. No, now that's on the rotated coordinate system. Any other questions about that problem? All right, so now we're going to get into rigid bodies. We're done with particles. So the definition of particles was objects that we treated as having no length dimension And you do that when you don't care about the orientation of the object. So now with rigid bodies, we're going to deal with objects that do have length dimensions. So now there are two things that matter that didn't before. So that brings up two new concerns. The first one is an object's orientation. And the second one is where on the body forces are applied. So like imagine a car on ice. So this is a top view of the car. You know what I mean? I'm going to just be drawing this car the rest of the class. Watch this though. Just do this in your notebooks. Okay, so if you if you're treating this like a particle, so think about two cases. One where you apply a 50,000 Newton force here, and one where you apply a 50,000 Newton force here. If you were treating this car like a particle and you didn't care about its orientation, the only equation that matters for determining the motion is Newton's second law, and it says the acceleration of the center of mass of the car is going to be the same in both of these two cases. So these two are both identical because we don't care about orientation, and that means we don't care about where on the body forces are applied. But if you do care about orientation, and often if you're sitting in a car, you care very much about the orientation, then you're going to get drastically different results from this and this. You know, if you apply that force at the middle of the car, it's going to accelerate without spinning. And if you apply that force at the front of the car, like that first picture, it's going to spin as it accelerates. So that's supposed to be just like an illustration of why, if we do consider orientation, and we are considering that objects have length dimensions, now where the forces are applied change the problem. No, there's a lot more. When you think back on this, you'll be like, wow, there was a lot more in what he said than just that. Okay. It's one of those things you're gonna sort of keep, the learning is gonna keep soaking as time goes by. You know what I mean? You'll be at the bus stop being like, oh yeah, I never thought about it that way. That kind of thing. So there's a key new concept that we need for rigid bodies. And that is the moment. People also call it torque. Usually physicists interchange moment and torque like they're synonyms. Engineers tend to think of a torque as a twisting of a rod about its long axis. I'm going to use the word moment, but in your physics class you might have called it torque. And even though people just call it a moment, you should think of it as the moment of a force about a point. The definition of a moment the moment about a point A is equal to a vector rho crossed with force vector. And I'll draw a picture and explain what these things mean. So this is the body, just some arbitrarily shaped thing. And a force is applied to the body here. Let's call this point P and the force F. And this point A is the point that we're calculating the moment about. So let me label these. This P is the point where force is applied. This A is the about point. The thing you're treating is sort of the axis of rotation. Then that rho vector is the vector that goes from A to P. So there's the rho vector. So rho is the vector to the point P from point A. And to imagine intuitively what a moment is, think about trying to turn a stuck bolt. With a wrench. And two things matter in how successful you're going to be at turning this bolt. One is how much force you can apply to the wrench. More force does help make it easier to turn it. And the other is how far from the axis of rotation you're applying that force. So, like if you apply a force F here versus a force F here versus a force F here, if you apply the force at the end than it is if you apply the force at the middle. And if you apply the force aiming through the axis of rotation, you can apply 1 billion pounds of force to that and it would never turn. All it would do is just rip the head of the bolt off. And so that's the idea of a moment. The moment tells you how, it tells you the tendency of the force you're applying to turn the object about that chosen axis, the about point. One thing to keep in mind, it's easy to forget this in 2 dimensions, is that a moment is a vector. And a lot of times we're going to write it like it's a scalar in 2 dimensions. But a moment is always a vector. with along the axis of the produced rotation. And if the thing isn't rotating, like in statics, nothing's going to be rotating. Imagine the rotation that moment is trying to cause. So even if this stays stuck, you know, so you're applying this force, but that's not going anywhere. That moment's still trying to produce a rotation about an axis into and out of the board. And so the direction of that moment is into or out of the board. I think sort of a useful organizational thing, and we'll keep going with this, and it won't be totally obvious yet why it's helpful, but as we go on, I think you'll like having it. So to organize moment calculations, I'd recommend writing out this table that has a column for the row vector, a column for the force, and then a column for the moment. That moment is just rho cross F. So this row vector is the vector from A to the point where the force is applied. And then that's the force, and then you just take the cross product of those two and it gives you the moment. Any questions about this yet? Okay, so let me do an example. So let's say we have a rigid body that has a height of 1 meter and a width of 2 meters. And let's say that there is a 1,000 Newton force applied down at the center and 2,000 Newton force applied up at the corner. And let's say our about point is here. What's the sum of the moments produced about that point A? Well, I'm going to use a standard coordinate system like this. And I'm going to write out this table. So we have a column for the row vector, column for the force vector, and a column for the moment. And each force is going to get its own row. I'm going to start out with this 1,000 Newton force. The row vector for the 1,000 Newton force is a vector going from A to where this force is applied. So what's the x component of a vector going from A to where this 1,000 Newton force is applied? Positive 1, yep. And what's the y component? Negative 0.5, yep. The force vector is in the negative y direction with a magnitude of 1,000, so 0, negative 1,000. Actually, now that I say it, I'm going to start out by doing these all in 3D. I was sort of using a shorthand, but let's do it like this for now. So the row vector was 1, negative 0.50. Force vector is 0, negative 1,000, 0. The row vector is a vector that goes from the point A, your about point, to the point where the force is applied. So to get from here to here, you have to go in the positive x direction 1, and in the negative y direction 0.5. Now the cross product is just, you can punch that into your calculator, but that cross product ends up being negative 0, 0, negative 1,000. We knew that it was going to have to be in the positive or negative z direction because both of those two vectors are in the xy plane. And we know the cross product has to be perpendicular to both of them. So when you're doing things in 2D, your moments are always going to have only non-zero z components. Then the second one, the row vector for that 2,000 Newton force. From A, you have to go in the positive x direction 2, in the negative y direction 1, nothing z. The force vector is 0, positive 2,000, 0. And the cross product is 0, 0, 4,000. So the net moment of A is equal to 0, 0, negative 1,000 plus 0, 0, 4,000. And it gives you 0, 0, 3,000. And the units are Newton meters. Any questions about that? Yep, in the z direction. In the positive z direction. So what that says is that the axis of rotation is in the z direction. So it's going to cause a rotation in the xy plane. You know what I mean? If you can picture the axis pointing out of that plane. Yeah, so, and it does it with the right-hand rule. I didn't get to all that yet, but yeah, the direction of that magnitude tells you how likely the thing is to turn, and the direction tells you if it turns, what's the axis it's going to rotate about.